Hello and welcome to the paper, Integrated Vector Field and Backstepping Control for Quadcopters. In this work, we present an integrated guidance and controller scheme to drive quadcopters in path-following tasks with obstacle avoidance and constant uncertainty rejection. The main contributions of this work rely on the integration between the vector field guidance and the nonlinear backstepping with stability proofs, the consideration of torques as control inputs, and the applications of a novel vector field developed by our group. The controlled system in this work consists of a helicopter with 4 rotors symmetrically arranged in a plane. Its movement is a result of the 4 individual rotors' velocities. This figure shows a schematic for the vehicle, where its center is a blue cube with the center of mass in the geometric center. A reference frame rigidly attached to the body is plotted in RGB. The control inputs are considered to be the total thrust Ut and the torques U-tau, which are given by the equations. The considered model for the vehicle is represented by the equations in the slide, where P is for the states of position, O for orientation, V for linear velocity, and omega for angular velocity. The problem addressed in this work is defined by considering the presented vehicle dynamic model, design a nonlinear controller that drives the vehicle with constant speed to converge to and follow a given time-varying curve with known parametric representation. The design controller must allow obstacle avoidance and be robust to constant uncertainties. If obstacles are sensed between the system and the curve, the controller must prioritize the avoidance over the curve following. This means that the system is allowed to move away from the curve to accomplish the obstacle deviation and then return to it once the avoidance is finished. For part of our solution, we use a vector field approach previously proposed by our group that allows path following with obstacle avoidance, considering the first-order integrator model in n dimensions. In summary, we propose a backstepping controller with integral action to solve the stated problem. The integral action will allow the constant uncertainty rejection. The first step of the backstepping will consist of a vector field from our previous work to accomplish the path following with obstacle avoidance task, finding a virtual control law for linear velocity. The second step will consist in finding a virtual linear acceleration. From there, we can obtain the total thrust and the reference orientation. Then, the third step will consist of a virtual control law for angular velocity. Finally, the fourth step will consist of the torques control input. We now show some of the simulation results using MATLAB Simulink and ROS. This animation was obtained from the results of the simulation performed in MATLAB Simulink. In this simulation, we have a time-varying closed curve and we add disturbances to the system at time 50 seconds. The system was able to recover from the disturbances and converge again to the target curve. The next simulation was performed in ROS and these results are animated using RVIs. In this simulation, we have obstacles on the way to the curve and we can see that the vehicle is able to deviate from them and then get back to the curve. In this work, we proposed a backstepping controller with integral action and vector field to drive quadcopters to a path-following task with obstacle avoidance. For future work, we propose to evaluate the robustness over bounded and unknown uncertainties to assure stability and to perform real vehicle experiments. Thank you for watching. We kindly invite you to read the full paper.